Well, hey everybody. I'm going to try to run through the first 11 pages of the notes on waves right now. What you're seeing here is supported by some videos both within and without the note, and those links are going to be set up here both within the notes, and those without are going to be right here on the home page on the physteach channel on YouTube. For example, there are two videos set up for notes page 2 to help support your understanding, and then for some of the other pages there will be videos posted as well. So we're going to try to run through this quickly. You may have to pause, try to limit the length of this video, and yeah, just follow the instructions. And really, you're going to be using this as it best serves you, and you're going to figure that out over the next few weeks, what that really means. Some of you need to cling on to every detail. Some of you really need to hang on to the bigger ideas. You think about how this might serve your future, and that's really the way to approach it. So there's an intro page 1 there. Read it through. It's pretty interesting. Basically, you see big ears and big eyes, and that has a lot to do with this unit called waves. All right, let's go over here. Page 2. There are 2 support videos on YouTube for this one. And so let's keep going on this. Fill in some notes, oscillation, vibration, so that movement back and forth. The key here is you need something shaking in order to then inspire a wave. So oscillations are the sources of waves. So let's go over here. Now, you saw this in the videos, and here also we have a couple of words that are helpful. Wave is a vibration or an oscillation that goes somewhere through space and time, so it actually goes somewhere. There are a couple types, pulse and periodic, and that's just, you'll see the type of the vibration here. So I'll give you a pulse. There's a pulse. So it's a singular traveling disturbance. It actually goes somewhere. This applet's pretty cool. The website is linked up here in the notes. You want to check it out. You got to download it, but it's easy. There are lots of pieces here that I'll extend with this later on. You can put a loose end on this. See how it comes back. Put a fixed end on this. Do the same sort of thing. See how it comes back. There are interesting differences here. But for right now, all you got to worry about is there's a pulse. Boom. Now, pulse is a singular traveling disturbance. There it is. Periodic, on the other hand, and again, let me remind you, I'm going to go quick, so pause as you need. Also, please do this on a computer if you have one available. Much better than doing this on the phone. So, periodic would be repeated. And so a word we have for that is oscillate. Boom, there it is. Let's decrease the frequency here. There it is. If you do this from a pulse perspective, that's like pulse, 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 repeatedly hitting that pulse button. It's a bunch of pulses in a row. But really, you notice these are not particularly symmetric. Not until you get this to oscillate. Now, you start to see this symmetric wave here. There's a symmetry to that. That's nice. Look at that there. Okay, that's a periodic wave. So periodic actually is a regularly repeating traveling disturbance. Continuous. Regular, by the way, is the same way you understand it in math if you've done that word strictly defined in math. The regular, like a regular polygon, is symmetrical. So this one technically is not because there's damping. In reality, there's friction in this scenario. If we take that out, then this wave really does become symmetrical. So the videos you saw in the backyard, they're more like this. Actually, they had a fixed end. They were more like this. Something like that. Okay, good. Let's come back over here. The last thing was the medium, and the medium is what the wave went through. Same thing that vibrates as the wave energy travels through it. That's all. So if you want a wave through a spring, the spring is the medium. The water is the medium for a water wave, and so on. So here's a few fancy words. Transmit, transfer, propagate. That just means move along. So the source determines the waves. The system type determines the wave type. This is real important. We went over this in that video also with the kids, and we'll talk about that right here. The rate of oscillation determines the rate of new wave arrival. Well, that makes sense too. If you come over here, you can look at that. I was messing with that frequency button. Let's go to no end again. It's easier to look at. If you notice here, there you go, settle down. New wave, new wave, new wave. I'm at the window here. New wave. And this thing is vibrating at that same rate. New wave, new wave, new wave. If we instead speed up the oscillator, you will speed up the rate of arrival. New, 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 new. So these are actually very important ideas right here. The type of system, the type of material, that determines the type of wave, and how quickly it vibrates determines how quickly new waves show up. Now, we talked about these, basically the Earth's crust. You get an earthquake wave, also called seismic waves. Remember that from Earth science. Seismic. Oh. Seismic wave. There you go. And those earthquake waves, also called seismic waves. Ocean, you get a water wave. Sun, you get a light wave, the electrons. Speaker shakes the air, you get a sound wave. And of course, crowd of people, there's the old Chase Stadium, you get a stadium wave. Okay, cool. So that just reinforces that point. The type of thing that's shaking gives you the type of wave that comes out. All right, let's go over here. A couple of things to notice, like what are these real quick? Of course, you could see this is a pulse, just a singular traveling disturbance. Another pulse here is this rope coming by the wall, another singular traveling disturbance. These others, though, periodic, they look like they're repeating. This water wave has a periodicity to it, a symmetric repeatability. Same with this slinky over here. This is a pretty cool one. A tuning fork is a good example of an oscillation. So here's one. It's a slow-mo video that I took years ago. It's actually a tuning fork. It's a camera that's filming 1,000 frames per second. And you see the ends of the tuning fork moving up, down, up, down, up, down. Interestingly, we had a different projector set up back then. This projector flashes between different types of light on the board. You can't catch us with your eye. It's way too fast. But there's a oscillating, tuning fork. Cool. These videos, by the way, these are all on the physteach. So if you want to go check them out, go check them out. Only 11 views. It could use a little love. All right, let's go over here. So the ends of this were just oscillating back and forth this way and this way. You could also say, however, there was a wave, and the wave actually traveled down the length of the tuning fork, hit the neck, and then came back up. So there's an oscillation. So there's an actual wave going down this way, and you get the oscillation of the top. Two are connected like that. Okay, next page. What do waves transmit, i.e. what's a wave's purpose? So you'll see there's a little support video down here for transverse versus longitudinal. So check that out on the home page, on the physteach page. Purpose of a wave. Boom. Transmit energy, and they do it quickly. So they transmit energy, they do it quickly. So a wave is telling you something. You could hold on to the end of a rope and somebody shake the other end, and when you feel the shake, that means drop and run, or that means come help me. Whatever it means. Somebody knocks on the door. There's a signal. Come open the door. So waves transmit energy, and the cool thing about them is they do it quickly. They can act like a signal. This is an important note. Waves transmit energy, but not mass. And this is totally related to the quickness aspect. Again, waves transfer, and you see we're using some synonyms here. Instead of transmit, we're using transfer. Waves transfer energy. Waves do not transfer mass. This is huge, 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 big. Please burn this into your head. It's one of those big concepts of waves. Waves are cool. They're really cheap and they're really fast. And the whole reason they are cheap and fast is this right here. It's because they can send something to you. They can send a signal. They can send energy, but no mass. And so it's like email versus regular mail. Email, there's nothing going from my computer mass to your computer. Basically, I'm sending a signal that bumps along in the power lines all the way through, and the note gets to you, the message gets to you very quickly, and it's very cheap. Regular mail, it requires papers, it requires people to pick it up and carry it. There's a lot more time and money involved when you're transferring mass. So waves are cool. They're real quick and they're real cheap, and that's why we use them. All right, how are waves classified? One way is to classify how they shake. So waves travel through the medium. If the medium is the spring, then they travel through the spring. If the medium is a pan of water, then they travel through the pan of water. However, you can shake that spring or that water in different ways. So a transverse wave, a nice way to remember this one. Well, first off, transverse looks like this here. Transverse wave, let's jump over here. It tends to look like an S or a snake. Here's a transverse wave. So watch here. This person will shake the spring, a little bit slow, but there's your transverse wave. Here it goes. Yeah, look at that. Isn't that nice? Now, what you're seeing plotted up here, we can also record the transverse wave. This is called harmonic motion, simple harmonic motion, which basically means it moves back and forth in a nice, easy way, in a symmetrical way. You can actually map that up here, and you'll see it comes out looking like what we call a sine curve. Sine or cosine, doesn't really matter, they have the same shape. And so there it goes. And so this is a model of what's actually happening in this rope or spring. And so this is showing you how much it's actually recording this red piece. How much is the red piece displacing from equilibrium? Equilibrium was straight across. How much is it displacing from equilibrium at each moment? So at some moments it's pulled up, at others it's pulled down. And we'll look more at that in a moment. So that is a transverse wave. Now a transverse wave starts with a T. Flip T upside down and you get the word perpendicular. A transverse wave is when the medium, that's the particles, vibrate perpendicular to the direction of wave motion or speed. So perpendicular direction, now that T, transverse, flip it over, perpendicular sign. What do we mean by that? Well, basically, if you go back to this little graphic here, the wave is going from left to right. However, the particles vibrate up and down. We'll show you that a few times. If you watch again, watch the red dot. That's the one of focus. You see the wave going to the right, but watch the red dot goes up, back down, then back up, and so on. So it's a pretty cool thing that this goes up and down and up and down. Meanwhile, there's something actually going to the right. And so the something is the energy. The energy goes to the right, but the particles go up and down. That's called the transverse wave. So how do we draw that? Well, your drawing is not going to be any worse than my drawing right now. That's for certain. A nice way to set it up, if we're just going to make one wave, put a dot at the beginning, put a dot at the end, put a dot in the middle, maybe somewhere over here. We can say it hits a peak in between these two. That's the nice thing about periodic waves. They're regularly repeating. They're symmetric. Going between those two, put a high point. Going between those two, put a low point, and then try to sketch this thing. Now, my sketch is going to be rough using a mouse pad, but let's try this. All right. Not terrible. Ran out of mouse. There you go. Okay, not too bad. So there's a couple of spots on this wave you should know about. First off, though, let's say the wave is moving this way. Often we call that the velocity of the wave. That's also the direction, the energy of the wave is going this way. So energy is going off to the right, but what are the particles actually doing? Well, let's label up a few spots on here. This spot, that is called a crest. That's a high point on a transverse wave. Drawing this is fantastic. Okay. In this low spot over here, see if I just type it out, that's called a trough. I know it's a weird word, trough. It's a trough. That's the low spot right there. Okay, maybe give that a little color. Yeah. So we get crest up top, trough down low. This blue line across the middle is actually equilibrium. You might consider that to be like sea level, if you want to use a water analogy. So equilibrium is right here. That's your sea level. Right along this blue dashed line. And so if you notice, parts of the wave get pulled up and down away from equilibrium as the wave goes to the right. So up and down are both perpendicular to right or left. And so that's called a transverse wave. So we'll do a quick little review here. you know, these particles, we'll put them at a few different spots. And make it yellow, you can see it. Here, here, here. Let's look at all these different spots. I'm going to give you a question that's going to bother some of you, but let's do it nonetheless. Even put one over here. Where are these spots going to move in the next instant is what I'm going to ask. Where are these spots going to move in the next instant? Well, it's kind of a tough thing if you just look at it. The mistake people make is they think that the particles are riding the wave. That's not what's happening. The wave is traveling through the particles. So actually a good way to think about it is grab this wave and move it over. Oh, what happens next? Well, really that means you got to look at the piece of the wave that's upcoming. This particle, for example, let me get back on red. This particle, for example, a crest is approaching it, which means in the next instant it's going to be pulled up. This particle, however, is already at the crest. It can't go up any higher. What's approaching it is here. A lower piece is approaching it, so it's going to go down in the next instant. This one, a lower piece is approaching it, so it's going to go down. It's almost like reverse what you would imagine. This one, a higher piece is approaching it, so it's going to go up. You're like, wait a minute, what higher piece? Check it out. Move the wave over a little, and look. The arrows start to line up. All right, let's go back over here. This one, a higher piece is approaching it, it's going to go up. This one, a higher piece is approaching it, it's going to go up. This one, a lower piece is approaching it, so it's going to go down. And this one, a lower piece is approaching it, it's going to go down. And if you can imagine here, the wave continues, it's a low piece, so this one's going to go down too. I know that seemed a little tricky. We'll revisit that a few times. Don't lose your mind over it. All right, our top two examples of transverse waves are light. You just have to trust me and memorize this for now. And S waves from Earth science. Cool, there's your transverse waves. All right, let's check out a longitudinal wave. Longitudinal wave, we had a little video for. Longitudinal wave looks a little different. Longitudinal wave, here we go. Longitudinal wave, notice this guy compresses the spring, and that compression moves along the screen. So he's moving back and forth, but the back and forth movement is different than it was last time. This time you compress, instead of shaking it up down, he's moving it forward backward. Now, one of the things worth mentioning here is we're still plotting it like a sine curve. But clearly this does not look like an S. The transverse wave, that looked like an S. The actual spring, the actual wave looks like an S. And we model it with a sine curve. A longitudinal wave does not look like an S, but we still model it with a sine curve. Notice here, this is the x-axis versus time. And so what's happening is these are being pushed forward, backward, and we're just modeling that here. Forward is positive direction, backward is negative direction. It's still what we call simple harmonic motion. And the wave particles still can be modeled with a sine curve. So be careful when you see a curve up here, like axes like this. Transverse axes, there they are. Longitudinal axes, it's the same pattern. And so you can't look at a model with scaled axes and be like, oh, I know it's longitudinal, I know it's transverse. No, you got to look at the actual medium, or you have to know something about it. So here, this is definitely not transverse. This is what we call longitudinal. The way to describe it is the medium, the particles vibrate forward, backward, while the wave is moving forward. Watch the wave. Here comes the wave. Wave's moving forward. But if we follow the red dots, they're going back and forth and back and forth. This is how the domino effect, in a sense, works with this. Dominoes that get back up. And so when the forward-back motion is aligned with the forward wave motion, you have a longitudinal wave. And what's the trick for remembering this? Longitudinal starts with an L, ends with an L. Two L's together make the parallel symbol. The medium, longitudinal wave, the particles vibrate parallel to the direction of wave motion or speed. Transverse, flip the T, perpendicular. Longitudinal, pair the L's, parallel. So how does that look? A common drawing of that is as such. I'm going to offset it a little because I don't want you to think it goes transverse to parallel. I'll put it over here. With a slinky, like you saw in our video, the slinky sometimes gets stretched out and at other points is compressed together. Try to keep the height the same, and then other times stretches out, and then squeezes together, and then stretches out, and so on. In this case, let's call again, the wave velocity is to the right, so the energy is moving to the right. And this energy is real. If you were standing here, you would feel hit by something. If you were standing here, you would feel hit by something repeatedly. And you'll see that in some of the future videos. We ask the kids about it. This one, we spend a little less time analyzing the locations, but the names of them here, we have a compression. That's really the name you should know. Often when they talk about longitudinal waves, they talk about compression waves. Anyway, the compression here, yeah, that's good. The compression here is going to be the area of the spring that is, no surprise, compressed. So the compression is going to be like this little piece, and the compression is also going to be this section here. And this one that's not as frequently mentioned is actually the one that describes this region and this region, although it's a good word, it's a good English word. It's basically, it's thinned out or spread out, which is sometimes used to describe high altitude air, or sometimes used to describe high performance athletes or musicians. They say they live in rarefied air or rarefied space. The word is rarefied. It's actually called a rarefaction. Rarefaction is that space where it's spread out. Now, usually you are not asked what direction do the particles move next, but it is a problem you could do. I mean, if we played that same game and, changing the text color. If we played that same game as we did before, and you said, well, where's this one going to go next? Or where's this one going to go next? Or where's this one? Any of these things, where are they going to go next? Well, you just need to think about what's happening around it. This one, it's on its right, it has a compression. A compression tries to push it away. On its left, it has a rarefaction. A rarefaction tries to pull it. So in the next instant, this one will go this way. This one has a compression on its left, a rarefaction on its right. It's the next instant, it's going to go that way. This one is kind of the reverse. It's going to end up being pulled this way. And then, you just repeat this whole game over here. And all of them go back and forth, just like you saw in this video over here. And I'll show you that again. But you see, follow the red. Forward, backward, forward, backward, all while the wave energy is moving along to the right. Okay, so there's your transverse longitudinal. Our top two examples are sound and P waves. I didn't want to say it before, but often a sound wave is called a compression wave. All right, cool. So there's a lot of these little footnotes here. You may want to check them out. They're pretty cool. All right, particle view. This is a fun thing to look at. Check this out here. This is a longitudinal wave. Do you see it there? So if you notice, there are these dark lines moving across the screen. And so clearly the energy is moving along to the right. However, if you look at any singular dot on here, like this one, any of them, they have the red ones there. Any singular particle, all it does is go back and forth. None of these, pick a black one to look at, it doesn't matter. None of these are actually moving net to the right. The energy is going to the right, but the particles are moving back and forth. That's what we mean by energy is transferred, not mass. That's what makes a wave quick and cheap. Here's transverse. Here it's very easy to see the particles just oscillating up and down, but relax your eyes a little and follow the humps. Follow the crests. You see the crests are moving along to the right. Water waves are often modeled as transverse. Near the surface, they sort of look transverse, but if you ever watch like a duck sitting on the waves, maybe you've been out on a boat, really the water wave is kind of a mix of transverse longitudinal. Follows kind of this circular pattern here. Here's Rayleigh surface waves. Look at this. Interesting one. This is earthquake waves. Notice both with water and earthquake waves, If there's a wave on the surface, the lower you go, the less impacted the material is. Okay, cool. Let's go back over here. All right, how are waves classified? Part 2. So part 1 was, we talk about transverse versus longitudinal. How are they shaking the medium? Part 2 is, well, what type of medium we talking about? So far, everything you've probably thought about and everything we've really visualized has been what's called a mechanical wave. A mechanical wave travels through a medium with mass, aka a material medium. Material media, like a spring, like water, like Earth's crust, they can support both transverse and longitudinal waves. That doesn't mean all waves are both, of course not. Some waves are transverse, some waves are longitudinal. But a mass medium can shake either way, depending on how the source shakes. Field waves sounds a little weird. These are waves that travel through any medium, but really the most important piece of this is including one without mass, the vacuum of empty space. So really the defining feature of a field wave is that fields are everywhere. Fields are in the vacuum of empty space. Fields are also in solids, liquid, gases. They extend everywhere in the universe. And so a true field wave can go through anything, basically. Field waves, however, are only transverse. Only transverse. The only types we'll really talk about, really the one we'll focus on, is electromagnetic. Gravitational waves are also field waves, but really electromagnetic's the only one for us. Anyway, what's the point of all this? You should be able to define or describe which way the wave vibrates the medium and what type of wave it is. And so let me run you through here right now. Normally we play a little game with this in class, but we'll use T for transverse, and we'll use L for longitudinal, and we'll use, let's see, transverse waves. Let's make them, why not? We'll make them red. Longitudinal, we'll make them blue. And then electromagnetic, maybe we'll make green. And mechanical, we'll make, let's do brown or gray. That's good. So let's check them out real quick. How do you go through them? Nothing too crazy. Here's what you got to know. S wave, well, it looks like an S. From that, you should know perpendicular, boom, transverse, done. S wave shakes the Earth. The Earth is made of matter, so it is a mechanical, transverse mechanical. A water wave that you surf, usually we model water waves as looking like an S, so that too, transverse, and water, of course, has mass, it's material, so it too is mechanical. Okay, cool. Let's keep going. Sound. I asked you to memorize. Sound is the prime example of a longitudinal wave. Remember it, memorize it, a compression wave. Sound, you might think, what does it shake? Well, actually, the sound we deal with most shakes air. Air has mass. Air is matter. So sound is a mechanical wave. P waves. P waves, actually, that's the other example you should remember of a longitudinal wave. P waves are longitudinal. P waves, boom, they shake the Earth, mechanical. By the way, in earth science, you did little charts on this in the reference table, the difference between the P wave and the S wave arrival times. Remember all that? And if you remember, S waves did not travel effectively through liquids. There were shadow zones. That's how we've figured out which parts of the Earth's interior are most likely liquid. Cool stuff. Anyway, light. Light was the prime example of a transverse wave. So all types of light are transverse. Now here, we also said light is, well, I don't know if it did say it yet. Well, let's say it now. Light is electromagnetic. Light is electromagnetic. In fact, we're going to need the PRT right now. So let's pop that up here. Let me bring that over here. You can always pull it up this way, by the way. Physics, reference table. And it should be, there it is, boom, PDF, nice view. You can look at it on your phone. Look at that, so nice, so nice. Okay, on here, you did W80. And the reason I wanted to do 80 is not because it was a headache. It may have been. But because once you get used to looking around. the electromagnetic spectrum, here it is, it has all these different types of light, one of which is visible light. Aha! Visible light is in the electromagnetic spectrum. Well, then it is electromagnetic. In fact, it's nice to realize that visible light is both transverse and, of course, in the electromagnetic table, so electromagnetic. But all of these other gray boxes are too electromagnetic. They are all types of light, just not visible. Visible means your eyes can pick it up. These others your eyes can't pick up, although we can sense some of them, notably ultraviolet and infrared. We feel the effects. But anyway, all these we have created devices to sense them for us. But all of these are types of light, which means if you see radio, that's sound, right? No. You need a radio device to interpret a radio wave in order for it to turn it into sound using its speakers. It has an antenna and speakers. Radio waves are here. Radio waves are actually types of light. Radio waves are transverse and electromagnetic. That's one that tricks a lot of people. How about X-rays? X-rays, you go to the doctor, get an X-ray. Guess what? Here it is. That's actually a very high energy type of light, which is why you need some protection from that. So it too is transverse and electromagnetic. Finally, ultraviolet. Ultraviolet is on this chart too, electromagnetic spectrum. It too is high energy. This whole end is very high energy. This end is lower energy. So this whole high energy end over here, ultraviolet, is type of light. It is transverse. And it too is electromagnetic. All right. Assuming the last four energies up here are electromagnetic, what can you say about electromagnetic radiation in general? A few things. One, you can say, let's shrink this down. It can travel through space, the vacuum. We said that up top. Number two, it is transverse. And actually number three, which you may not realize, is they travel at the speed of light. Cool. All right, at what speed do electromagnetic field waves always travel in empty space? Well, at the speed of light. Boom, at the speed of light in a vacuum. PRT1, there it is. Speed of light in a vacuum. Sometimes we call it C. You can also call it V because it is a speed, and it's 3 sig figs times 10 to the 8th meters per second. There it is. All these things travel at that. Good. Note, mechanical waves like sound, this is real important, require a material medium and cannot pass through a vacuum. You ever watch some of those movies like Star Wars and they got them shooting at each other, and when the camera is supposed to be out in space filming them shooting with the pew pew, they're lying. There is no sound. There is no sound. In space, the only way you can have sound is you need a little pocket of air you bring with you, like inside the ship. Inside the ship there is sound. And if this blaster hits the ship and shakes the ship and causes it to vibrate, those vibrations of the ship will then vibrate the air around you in the ship and make a sound. But outside, as it passes by, nothing. And if the ship explodes and you are outside of it, you too will hear nothing. Okay. Here's a little motion hierarchy. So you might dig this. You know, check it out if you want to check it out. It's not something to worry about right now, but these are all the different, like, what happens. Motion, this whole course can break down to motion for a lot of it. This is like translational motion that we talked about the first part of the year. Here we now have motion where you come back to the start. This is like a pulse, an oscillation, and then all the different types. You may like this. All right, all this empowers you to do 8-1, and for that one, I'll give you some instructions when we get to that. All right, let's keep going over here for a little bit. How are waves modeled on paper in 2D? All right, so we can't just talk about waves, we model waves. One of the ways we model waves is drawing them. We have the profile view, which is called the side view. So we're often writing on paper, and so you're writing on paper, you got to be able to know what you're talking about. So let's model transverse and longitudinal on paper. One way we model transverse, well, on paper you make that snake. So here we're going to make it more than 2 humps, or more than 1 up, 1 down. Last time we did 1 up, 1 down. Now let's put an up, a down, and an up. How can we do that? We can split this into 3 equal pieces. Remember, these are all, for our purposes, periodic. So I'll say maybe a split here and a split here. It's about equal. Okay, cool. This time I'm going to start with a trough. Why not? You can. So let's say, remember, symmetric, going between the two, drop down. I'll put my trough here. Then we'll have a crest around here. And then we'll have a trough again around here. All right. Then connect the dots. Oh my goodness, not beautiful. However, lucky for you, as long as you actually get this thing looking periodic, you're okay. You're okay. You actually can make triangular waves, and you will have to draw them. You can actually make a triangular. It's not a big deal. It's all good. Okay. So there's our transverse wave. There's a profile view. If you remember, just a couple labels. We had the trough. We had the crest. We had the trough. Actually, I'm going to move my crest label up here. We chose we can have energy can go left or right, doesn't matter. And most people like to do it right, so we could have the velocity of the wave going to the right, which means the energy is moving to the right. But the particles here, of course, vibrate up, down. So if you remember that, let's do a couple of spots. Here, here, space it out a little more evenly. I know this is a hard one to get, so we'll say it a bunch and hopefully it starts to sink in. Like, pick this spot. What's approaching it? Something below it, so it's going to be pulled down in the next instant. Pick this spot. What's approaching it? Something up, so it's going to be pulled up in the next instant. This one, what's approaching it? Something down. It's going to be pulled down in the next instant. What's approaching it? Something up, so it's going to be pulled up in the next instant. This one, the wave would extend, so something up, so it'll go up in the next instant. This one, something above it is approaching, so it'll go up in the next instant. And this one, something below it, so it will go down in the next instant. And hopefully my drawing's not too bad, that if I actually move the wave over, it'll line up. Let's try it. Not bad. Not bad. So notice, this one would have dropped to here, to here. This one would have moved up to here. This would move up to here, down to here. Actually lined up nicely. So you move the wave over and boom, that's what you got. Cool. All right, longitudinal, there's a couple of ways to draw it. One common way to draw it is the same way we did before, which is like the spring version, the slinky version, which was rarefaction, compression, rarefaction, compression, rarefaction, and so on. And then the compression will start here. So if we're going to label these up, this is your rarefaction, this is your compression, rarefaction, compression, rarefaction, and so on. Okay, again, we can say that the wave motion, let's call it to the right, that's the velocity. The energy is traveling off to the right. Good. We get those vibrations back and forth. In case you want to see that, like some of the easier points would be right here. The compression pushes it away and the rarefaction pulls it towards. So this one would go here next, whereas this one would go here next, and so on. All right, another way to draw longitudinal, a nice one, is sometimes it's drawn as like a column of air. We can leave this. Here we go. Sometimes it's drawn as a column of air. So you'll see like a tube like this, and like this. And like this could be the body of a clarinet or whatever, any sort of instrument. And they'll draw the particle view. And so the particle view looks like this. We'll line it up with this business down here. So up, this is all rarefied. So you just have, here's the particles, the air particles inside the instrument. They're kind of thinned out over here. But then where the compression wave is, they are very close together. This is joyous to draw with a trackpad. So here, These air particles are compressed, 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 compressed. You know, it would really be nice if I could just copy and paste this right here. Let's see if they'll let me do it. Yeah. Oh, oh, too fast. And so you get the same sort of business here. Rarefaction, compression. Same sort of business here. Rarefaction. The compression is just beginning. So let me clean that one up. And I can finish filling in this rarefaction over here. It's actually a little more compressed on this side. So you get a pattern kind of like this. So just beware. That is still showing you a compression wave or a longitudinal wave. All right? Even I've seen this drawn, and then it's not really drawing the waves, but even I've seen this drawn. Move it up a little. Oh, we move it up. There we go. Even seen this drawn with lines. Something like, I'll keep it perfect, like this. But if it's spaced out, and then close together. Oh, and then spaced out. You've seen patterns like this. But don't get too crazy, because basically you're looking. Do you see spread and then compressed, rarefied, compressed? You get an idea of what's going on. Okay, clean that little piece up right there. All right, good. So different ways you see longitudinal waves expressed. Beware, I showed you before, everything can be analyzed with a sine curve. You really got to watch out for this. Everything can be drawn this way. So when you see axes, don't get excited. You see numbered axes, don't assume transverse. You'll start to learn as we're going on here, you know, is that something that those of you who not going to be spending as much time with mathematical science need to worry about? Maybe. In a generic way, yes. But technically here, not as important. Those of you going on, you better watch out. You better watch out, because this here could represent, let's say, a crest, but it also could represent a compression. This here could represent, let's say, a trough, but this could also represent a rarefaction. So don't be excited when you see this. Oh, it looks like an S. It's transverse. Slow down. All right. So here was a profile view. Now we need the aerial view of waves. Big note here. Both wave types look the same from above. If you are truly above and looking down and everything appears two-dimensional to you, you don't know if you're looking down on compressions or crests moving across the medium surface way down below. So there's a few words you got to know about. One word is wavefront. I'm not having you write them. It's just, let's see what they are. Wavefront is a line of matching points. Corresponding points means matching points on adjacent waves. All right, we'll see what that means down here, because that's like a little wordy for where we are right now. A ray runs perpendicular to the wavefronts, starts at the source, tells which way the wave's going. So let's check this out. To put these into action is a lot easier. This is a piece of wood being bobbed in and out of water. Let's say there's a water tray here. This is the source of the waves. This is the thing that is oscillating. It's then making the water oscillate, and when water oscillates, you get these disturbances that travel away called waves. You get water waves. So if you want to draw a ray, here we go. Let's pick a color. Here is a ray. Start at the source and point away. Stay perpendicular to the wavefronts. This would be wrong. So we're going to undo that one. But this is correct. This, by the way, is wrong too. It's not starting at the source. It's starting in the other way. It's coming toward the source. This one is okay. There's a ray. Here's a ray. Heck, you could even start it over here. Here's a ray. They're not particularly picky about whether you literally extend it to the source, but to be safe, it's best to do it that way. So I'll bring this one back. Those are all rays. Okay, cool. Realize they start at the source. They tell you which way the wave is going, so they need an arrowhead. Just to be clear, this is not a ray. It has no arrowhead. It doesn't tell you which way it's going, so that's not a ray. And they're perpendicular to the wavefronts. That was the first one. These are the wavefronts. So what this could be, if this is water we usually model as transverse, then this could be a crest. In fact, probably the nicest way to try to look at this is to imagine this as a little bit profile. It's not profile. This is aerial view. But if you imagine this a little bit profile, then you can kind of imagine that like crest, trough, crest, trough, crest, trough, crest, and so on. You can't actually see that from straight above. But if you imagine if that's what's really happening, and then that's happening with all these right next to each other in a row, then the view from above really is just these black lines. But do you see how it's all the crests line up, and that makes one of the lines? So this here is really a line of crests, crest, crest all the way down here. So maybe we call this, we'll name it at the bottom. It's a line of crests all the way down here. The next line of crests happens here. The next line of crests happens here. The next one here, and so on. Troughs happen in between the crests. That's what we're drawing here. Crest, the next crest, the troughs in between. So where will the troughs line up? Well, let's switch up our color on that. Make them blue. The troughs will line up like right here. So all along this dotted line, notice here, you see a trough right there? And they line up all the way through. So these are your troughs. And then here, your troughs all line up with this spot. And here, your troughs all line up with this spot, and so on. By the way, those of you going on in this, if you're not, don't worry about this. Those of you going on in this, there's no reason to make the lines crests and the spaces troughs. That's just a random choice. You can switch it. The lines could be the troughs and the spaces can be the crests. It's fine. It's the same order of business here. Okay, so we had to draw 2 rays. We made 3. Label crests and troughs. We did that. And actually, before we go on, let me show you a little simulator. Up here, this is just like what we just saw, except rotate the whole picture 90 degrees. And here we go. So you basically have a stick bobbing in and out of water, and it's making these new wavefronts, these plane wavefronts. From this view, you definitively cannot see, is this transverse or longitudinal? We don't know. You can't see. Now, if we take a 3D view, let's bring the brightness down a little bit, and imagine if you were in, let's say this is water. I know up here it says waves is sound, but that doesn't connect to anything here on this graphic. If you were in the water, let's say you were here floating and bobbing, you would, hey, crest, trough, crest, trough. The waves would come by. So here you can tell. Profile view, you can tell if it's transverse or longitudinal. Aerial view, you can't tell. Someone needs to actually say, oh, these are water waves. Oh, these are sound waves. Oh, those are light waves. Okay, cool. Now, last question. Using a ruler, determine the distance between successive wavefronts. So wavefronts are where the matched up crest, the next match up crest, the next match up crest. So here's a ruler. I think it's scaled about right. Successive means one after the next. Do not use the first wave. And what I mean by that is this. This bobber makes a wave. Let's say it makes a new wave every second. Has a full second passed, guaranteed, since this last crest was made. If you look at the spacing from the bobber to the first wave front is about 6 millimeters. From the first to the second is about 9. From the second to the third is about 9. Third to the fourth, 9. Fourth to the fifth, 9. Aha! Do not use the first wave when you are measuring this distance between successive waves. So you can use the second to third, third to fourth, fourth to fifth, doesn't matter. But don't use the source to the first. So here I'm getting about 9 millimeters. So the distance between them, you can write this, I'll estimate it as 9.0 millimeters. You may find it to be slightly different. I remember there being some contention on this. This would be 0.90 centimeters, and this would be 0.0090 meters, maintaining two sig figs here. 0.0090 meters, which of course is the same thing as 9.0 times 10 to the minus third meters. I wonder, how do we superscript, subscript? Oh, it works. Good. Get rid of that nonsense. Good, good, good. Okay. Now, another example of this is real life example, these planes. So, you check this out. These planes, it's like World War II planes maybe, flying over the, or World War I, sorry, flying over deep ocean here. If you notice these lines, those lines are the wavefronts. So we can roughly approximate them here. Let's make them red. Here's a wavefront. Here's a wavefront. Here's a wavefront. Here's a wavefront, and so on. So you get all these wavefronts. Now, what can you draw? You can draw a ray. You can't tell from this picture, actually, but if we assume out here, let's assume this to be maybe deep ocean, and let's assume the wind is blowing in this way. To draw a ray, you would have to draw it coming from the source. Let's say the wind is coming from the deep ocean. The ray would have to be perpendicular and come in the direction of wave motion. I know it's hard to imagine perpendicular here, but because this is an angled drawing, this is actually what perpendicular would look like. These actually are right angles. We're just off to the side. So let me come in here and draw this thing. Your right angle, your right angle, your right angle. All right, it's a perspective drawing. You like that? Okay. And so this could be a line of crest, 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 all the way across. And then this could be a line of, let's undo that guy. Troughs, all the way across, troughs, all the way across here, and so on. A version you have probably seen, you've never seen this live, version you've seen is this one. Perhaps if you've flown into some place with water, maybe flying into Florida, or it looks like maybe Hawaii or some kind of volcanic island. Here, it's a little more rippled along the wavefronts, and that has to do with the ground underneath and the winds and interacting with the surface of the sand under the water as it's changing depth, and also the winds are bouncing off the land here. So you get a lot of causes of turbulence. But anyway, you still can roughly see this. You know, here you got like wavefront, 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 roughly speaking. And you can draw yourself the ray here as well. Here often the winds are coming in, daytime winds, the sea breeze. So the ray is coming in this way. All right, cool. So let's go back over here. All right, we got all this business. By the way, this distance between waves, it actually has a name. It actually has a name. That name is, see if anybody knows. The name is actually the length between waves, aka wavelength. That's actually what this is. So I might as well tell you what it is as you're doing it. That's called the wavelength. The wavelength. Pretty cool. So there's your wavelength. The wavelength has a funny symbol called a lambda. And pull that up on the PRT because it's hard for me to draw it on this one. The wavelength, which you did, there it is, wavelength. That's a Greek letter, a lambda. People sometimes call it lambda. I'm trying to work on it for Greek friends. Help me out with the pronunciation. Thank you. Okay, let's go over here. Now, one last one. There's a video. It's a pretty cool video. The title of the video, You can go search it, but it's desert insects, scorpions, and snakes use special skills to survive. 4 minutes. Actually a fun video. Check it out. I'm not playing it here because I'm not getting hit with that copyright. But here, actually, it's a pretty cool thing. Start putting in these QR codes in your notes. If you literally, even with the computer screen, hold your phone camera up to it, it will recognize the code and it will bring you automatically to the YouTube on your phone. So if you're doing this on your computer, boom, put the phone up there, bring you right to it, and you can watch this little video. And this video connects very much to the ray. So I would say pause, go watch the video. Okay, you're back. Pretty cool thing is that the scorpion aligned its body to actually find the ray. And once it was lined up perpendicular, it could follow the ray directly back to the meal, to the beetle. Now it happened to get snagged by a snake doing the same thing. But it's pretty cool that actually intuition for the ray finds the source. And we are not that good at finding the source, particularly when it's sound. You know, if it's laser light, we do a little better. But sound's very hard to locate. You know, when you're in a room and somebody's talking to you, it's pretty easy, trial and error. You turn around and you'll see them. But if you're in a house at night and one of the smoke alarms goes bad, the batteries go bad and it starts beeping, chirps once a minute, it's very hard to identify which one it is if you have like 5, 6, 7 of them around the house. So finding the ray is not automatically an easy thing. All right, so this one, it asks you to measure these, make 3 wavefronts separated by 0.3 centimeters. So what we can do here is come, put a ruler on there, put a dot, 1, 2, 3, that's 3 millimeters, another 1, 2, 3, that's 6, 1, 2, 3, that's 9. I can do it over here, 3, 6, 9. I can take my ruler, rotate it 90 degrees. I got a little bit off 90. Line this thing up and play the same game. You see why I'm making these dots. So 3, 6, 9, 3, 6, 9. And then connect the inner ring, middle ring, outer ring, and you'll actually have 3 wavefronts. Let me see if I can get away with using this circle maker. Yeah, let's try it. Let's try it. Come on, circle maker. Oh, it actually works from the center. Kind of digging that. It's reasonable. There's the first one. Not perfect, but close enough. Let's do our second wavefront. And then our third. Good. It looks a little off kilter. And sorry, you got to do it freehand. But there you have 3 circular wavefronts, roughly separated. The middle one still looks a little small. Roughly separated. Let's see if I should grow it slightly. A little better. By 3 millimeters. And so you have actually a wavelength of 3 millimeters, 0.3 centimeters. Draw a couple of rays on there. It's easy enough to do. So you have ray. Remember, from the source and perpendicular to the wave, it doesn't matter. There's plenty more than 3. You can draw as many rays as you want over here. So I just drew 3. It's the question asked. Boom. That distance, by the way, not bad to mark off. From here to here, same thing as from here to here. Don't do the middle one to the source, even though you measured it right. That distance is called the wavelength, lambda, and that is 3.0 millimeters. There you go. Okay. And that, if you come over here, I think if we reset this, it automatically defaults. There it is. Here's your circular wavefronts. We can slow it down a little, bring the frequency down a little. And this is like throwing a rock in a pond. If you 3D this thing, Pretty cool, right? Surface of the water looks something like that. No damping, so when you put actual damping in, in the pond, you actually get something more like this. The biggest splash or the highest splash in the center, and then as the rings spread out, they really thin out. All right, cool. That helps you with 8 too. Now, let's do a pause here, and then we'll pick up pages 7 through 11 in the next one.